Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to continue with an introduction to equilibrium, but here I'm going to focus on ice tables. What are ice tables? Well, you will probably run into a problem where you have to determine what your equilibrium concentrations are, but the only thing you know or are given is your initial concentrations of your reactants and products. So how do you go from your initial concentrations to your equilibrium concentrations? Well, one of the devices or techniques is to use what is called an ice table. I stands for I initial, C is for change, and E is for equilibrium, ice. And so what you're going to do is you set up a table. Now, you have to have a balanced equation. So that's the first thing you're going to need to make sure you have is a balanced equation. If they don't give you one, then you've got to somehow get that from the information you're given and set that up. So once you have your balanced equation, you can write a table. Now, you don't have to draw the actual table. You can set it up that way. Hold on just a second. Sorry about that. Light went off again. Okay, so you can just set it up without the boxes. You can just write in different columns, and so you're going to have three rows. One is going to be for your initial concentrations. The second one is for whatever changes are going to go on during the equilibrium process, and E is for your final equilibrium concentrations. And so you're going to have a column for each substance in your balanced equation. Now, if you have something that's a liquid or a solid, as we saw in the other videos, those aren't going to participate or affect the rates or the equilibrium of the reaction. So you can leave those blank or put a dash through the box. So if it's a liquid or a solid, you're going to put a dash to the box, and we're going to ignore that substance. We're going to ignore that species in the balanced equation and only focus on things that are gas or aqueous, because those are going to have concentration changes, and so we want to focus on those. And so this is basically the simple setup of your ice table, and then you just start filling it in, and then you figure out what your equilibrium expressions are going to be in terms of x, and then you solve for x using your equilibrium constant expression, right? Your KEQ is equal to your concentration of products over the concentration of reactants, and then you plug it in. So I know this is probably the first time you've heard of this, or if not, maybe I'm going to go over a couple of examples to kind of show you the steps to go through when you're solving a problem like this with an ice table. So I'll go over a couple of problems, and so we'll get started on the first one. Okay, so here's my first practice problem to go over. So I'm going to go over this in steps, and I'll point out a few things along the way that you're going to want to pay attention to. So here's the first practice problem. If your initial concentration of PCl5 is 1.3 molar, what are the concentrations of the products at equilibrium? So assume here that their reactants products are aqueous, and they give you the KEQ for this reaction is 78.3. And then you have the balanced equation. All right, so a couple of things. When if they don't give you the equation, you got to write it out yourself, balance it, and then you start with the equation and you set up your ice table. Now I'm going to set up my ice table without drawing the boxes to show you how you can do that. So what I'm going to do is on the side here, I'm going to just write I, C, E, give myself a little space here. And then I'm going to treat each substance with a column, and I'm just going to write the stuff along following the rows here without drawing. So the first thing you want to do is write your initial conditions, write your initial concentrations. And the one thing I want to point out is when you're doing an ice table, your substances have to be in concentrations, in molarity, right? If they give you moles, you can't put moles into your ice table. It's got to be in concentration. It's got to be in molarity. So if they give you the moles of your substances and they give you the volume, then you're going to have to use that to calculate the molarity and then put that into your ice table. Here they gave us the molarity of our reactant. We only have one reactant. That's the molarity they gave us. And the assumption here is since they didn't give us any information about the products, is that we're starting off, therefore we're starting off with zero concentration of our product. So we're given a 1.5 molar solution of this, and we're assuming we have zero of this to begin with. So I'll put 1.3 there. You don't have to write the molar there, it's assumed. So I have 1.3 there, and then these are going to be 0. So that's my initial, those are my initial conditions for these substances to begin with. Okay, now there's going to be a change. So because I know that I have 0 product, according to Le Chatelier's principle, it's going to shift in the direction to make product. That's the only way it can go. So I know it's going to shift this way, right? So what I'm going to do is for my change, I'm going to use X as a kind of a placeholder for that change. So I know that the reaction is going to go this way, right? Because I have 0 concentration here to begin with. It's at equilibrium, but I don't have any products. So it's got to make products. So initially it's going to go in this direction to begin with, right? Now I'm being redundant. Initial, begin with. Okay, I'm glad you're with me. Okay, so what I'm going to do is I know it's going to shift this way. So some of this is going to react to make some of this. So I'm going to lose some of this. So how much? I don't know. That's my X. So I'm going to lose some X, negative X, minus X. So I lose some X here, and then I gain some X over here. That's my change. So over here it's going to be positive. So I'm going to put a plus X. So I'm going to gain some X here, and I'm going to put some X here. I'm going to gain some X there. Now, another thing I want to point out that's really important. Why do I put negative X here, positive X, positive X? First of all, negative means I'm losing. So if it's going this way, if the reaction is initially going to be going this way, then I'm going to lose some of this. So I'm going to subtract X from this part, and I'm going to add X here. But also, notice that the balanced equation I have here is 1 to 1 to 1. The mole ratios are 1 to 1 to 1. Your X values must also be in that mole ratio. So you have to use the stoichiometric amounts for your X's. Since I have 1 mole of this reactant, PCl5, creates 1 mole of each of these, then 1X is going to form 1X here, 1X here. If this was a 2, right, if this was a 2, then I would have minus X here, and this would be plus 2X. Because for whatever amount I lose here, I'm going to gain double the amount here because of the mole ratio. So whatever your X's are, you have to use the same mole ratios or stoichiometric amounts for your X's. Since this is 1 to 1 to 1, then my X's are 1, 1, and 1. Okay, so now I have my change. So what you do to get your equilibrium expressions is just add these together. So 1.3 minus X. So this is going to end up being 1.3 minus x. So whatever x is, I'm going to subtract that from the initial. I'm going to end up with whatever the equilibrium amount is in terms of x. And then here, 0 plus x is just x, and 0 plus x is just x. So there's my ice table filled out with the change in x. And so my equilibrium concentrations are given in terms of x. So if I could solve for x, then I could then use that number, whatever x is, I could subtract x from 1.3. That would give me my equilibrium concentration. And then whatever x is, that would be the concentrations of my PCl3 and Cl2, right? Okay, so what do I do? So I filled out my ice table, and the next thing to do is to write your KEQ expression for the reaction. So here, here's my reaction. So I'm going to write my KEQ. So my KEQ, and that's going to be equal to the concentrations of the products over the concentration of the reactants written with their coefficients to their powers, right? So I'm writing the powers, I'm writing the coefficients as powers. So they're raised to the power of the coefficients. So here I have, so this will be the concentration of PCl3 raised to its power, but its coefficient is 1, so that's just going to be a power of 1. We don't write the ones. And same thing for the chlorine. So multiplied by Cl2, and then raised to its power of its coefficient, which is 1 again, so we don't write the 1. And then all of this is going to be over the reactant, which is PCl5. So the concentration of PCl5. Okay, so now I have my equilibrium expression for KEQ. And so now what I can do is I can plug my equilibrium expressions here into the equilibrium expression here. So remember, this only holds for when you are at equilibrium. And so my concentrations for equilibrium are here, but they're in terms of x. I'm going to plug that into my equation. So then here, so my PCl3 and Cl2 are both x, so it's going to be x times x over, and then PCl5, that's your 1.3 minus x. So I'm going to have 1.3 minus x. And so this is the next step. So now I have my equilibrium constant in terms of my expression in terms of x. I know what my equilibrium constant is. They gave it to me, 78.3, right? So now I'll write that over here, 78.3. So 78.3 is equal to this expression here. So now what I can do is I can solve for x, right? And then once I solve for x, I plug that in here, and then I'll have my equilibrium expressions. So that's pretty much how you do it. Now, a few things I want to point out, and I'll continue to solve this. Look at your KEQ. Your KEQ is much larger than 1. If your KEQ, if your equilibrium constant is larger than 1, then that means it's going to be heavily favoring your products. Why is that important? Well, that means that your x, your change here, is not going to be small. It's going to be pretty large. So there is a rule called the 5% rule. You can check using the 5% rule, and I'll talk about that in a moment. But you can't use the 5% rule if your KEQ is larger than 1, especially if it's much larger than 1. So here, the point that I want to make is if you pay attention to your KQ and your KEQ is larger than 1, and even if it's much larger than 1, that indicates that the products are heavily favored. So this is going to be pretty large. And so in this case, you can't assume that X is small. If we could say, oh, look, X is going to be so small that it's really not going to matter if you subtract it from 1.3. Like if X was really, 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 really small, then like if this was like, 0.0000000001, right? And you subtract that from 1.3, it's still going to be 1.3. So you can ignore it. It's so negligible that you can ignore X here. So you can simplify by just saying, hey, 1.3 minus X is just going to be 1.3 practically. So just get rid of X and make it 1.3, and then you make your math very much more simpler. But in this case, we can't do that because we know that it's going to be heavily favoring the product. So your X is going to be pretty big. So it's not going to be negligible. So in this case, you got to solve it using this expression here, which means you're going to end up with a quadratic equation, and you're going to have to use the quadratic formula. So I'm going to have to show you how to do that using this example. And then my next example, I will show you how you can assume that X is small. So let's go ahead and show how to solve this using the quadratic formula, and we'll go to problem number 2. So here I'm going to have to solve this I'm going to have to make this into a quadratic equation. And so what I'm going to do is, do I have space here? Maybe I do. So I'm going to multiply both sides here and here by 1.3 minus X. So when I do that, so I'll have, 1.3 minus X, and then I'll multiply this by 1.3 minus X. And so then I'll end up with 1.3 minus X times 78.3, and that's going to be equal to X squared. So this is X squared, right? X times X is going to be X squared. This is going to cancel out. All right, so now you can kind of see how the quadratic equation is coming about. I need to do the FOIL here. I need to distribute this, multiply it out. And so when I do that, give me a second. So I'm going to end up, if I multiply this out, I get, what did I get? So I'm going to get 101.79. And then I'm going to get negative 78.3, negative 78.3x, because negative x times this gives me this, and that's going to be equal to x squared. And now I bring everything over here to this side, and so I'll end up with x squared is equal to, oops, sorry, not x squared, 0 is equal to x squared plus 78.3x minus 101.79. And so here I have my quadratic equation, and so I'm going to have to use my quadratic formula to solve for that. So the quadratic formula, just to remind you, is that x is going to be equal to negative b plus or minus the square root. Did I give myself enough space? Excuse me. B squared minus 4ac all divided by 2a. And just to remind us what the a, b, and c are, your A, B, and C are the coefficients in front of the x here. So this is a 1. I'm going to write that. So this is A. And then this number in front of this x is B. And this doesn't have an x. This is C. So A is 1 here. B is this number in front of the x. And then this is your C. You basically, and then you, this is negative. So you're going to take that negative with it. And so you would plug in your A, B, and C into the formula and solve like so. So here x is going to be equal to, let's see, what do we have? So this is going to be negative 78.3 plus or minus. And then my B here, 78.3, so it's going to be 78.3 squared minus 4 times A, which is 1. A is 1, multiplied by C, which is negative 101.79. So negative 101.79. And then all of this divided by 2 times A, which is 1. And then you get x is equal to, when you solve that, you get 1.28 or negative 79.58. Well, x is supposed to be a change in concentration or a number. So you really can't have a negative for x. So x is not going to be this number here. So this is your value for x. Now that we have x, we can plug x into our values here, and we'll get the equilibrium concentrations. So then you subtract 1.3 minus x, so 1.28. So for PCl5, the concentration of PCl5 is going to be equal to, well, 1.3 minus 1.28 is going to give you 0.02 molar. Oops. Let me scoot that over. So PCl5 concentration is equal to 0.02 molar. And then we have PCl3 and Cl2, which are going to be x 1.28. So for PCl3, that's going to be 1.28 molar, and Cl2 is also going to be 1.28 molar. So those are the equilibrium concentrations for those reactants and products. And again, as I said, the KEQ value is very, very large. So that indicates that it's going to favor the products. It's going to favor the products a lot more than the reactants. And that's exactly what we see. We see that your reactant ends up with a small molarity, 0.02 molar, and your products, both of them, end up with almost the same concentration as the what we started with the reactant, right? So almost all your reactant became product, which is what would be expected if you have a Q that's very large. Okay, so let's do the next problem where our equilibrium constant is going to be very small. Actually, I just realized I don't have time in this video to do another problem like this. So I'm going to stop here. So this is a good example of what to do when you have a large KQ. Now, there's another way you could do this. there's a couple of things you could do that I'm not going to go over too much in this video or show you how to do, but I will talk about it a little bit. The first thing is, if you don't want to do the quadratic formula and you can't assume that this is small, another method you could do is called successive approximation. And what you do for that is to take your x value, right? So let's say you can eliminate x, right? Because, okay, so it's not going to work. You can eliminate x and then calculate what these x's would be. So eliminate this x, make it simpler, solve the equation for x using x squared equal to your 78.3 divided by 1.3, right? So you would solve for your x using the simplified version with x squared over 1.3 equal to this. So that's a much simpler equation to solve. You don't have to use your quadratic formula. So then you would solve for x. That x is not going to be correct. So what you do is you plug that x back in here and you subtract that x from 1.3, and then you do the calculation again, solve for x again, and then you plug that x in again here, subtract that x from 1.3, solve for this x here again, and you keep doing that over and over again until you get the same number back, right? So you want to do it until you get maybe 3 digits that come back each and every time. So once you start getting this, once you get the same number repeating, then you stop and you know you've reached x. So that's a useful way, a useful strategy for solving for x as well. If you don't want to do the quadratic formula, you can just do a successive approximation, again, where you go ahead and just eliminate x, assume it's small, right? So, I'm going to assume it's small, it's negligible. And then you can solve for x, plug that into the equation for this x, subtract, solve for this x, then plug that x into here, subtract, and you do that until you wind up with the same number after the, if you wind up with the next number being the same as the previous one you got, then you can stop. So that's something that you could do. Another thing I want to point out is another way you could do this problem is you could assume that all of this reactant becomes product. You could assume that first. You'd have to change this to moles if you're given the concentration. But you would say, okay, well, I assume that all of this 1.3 is going to form product here. And then you could figure out what the, assuming all of this reacts, well, how much product would that form? And you could calculate the concentrations of those and then start with those concentrations instead. And then instead of going this way, your reaction would go this way first. And so you could do the exact same thing. The only thing is your change would be different here. So instead of being positive on this side, you have a negative x, positive x. And so then these whatever these concentrations are, you'd have these concentrations minus x, this concentration minus x, and then this would be 0 plus x, and you'd have x on this side. So, and then you could just do everything that you did before. So that's another way you could do it as well. So that's it for this video. I hope this was helpful. In this video, I did a problem where you couldn't assume that x is small. You couldn't get rid of that, so you had to use a quadratic formula to solve it. But in my next video, I'm going to go over a second practice problem where you can assume x is small, and then you can do your 5% check to make sure. So, hold on a minute. So, if you like this video, please like, share, subscribe, hit that like button there, subscribe to my channel, hit that notification bell, and also when you do, make sure you hit all so you see all my videos. and then put a comment down below. Thanks for joining me. Have a great day.